Okay, so in this video I'm going to do a quick example on work done based with springs. So we're going to calculate the work done it takes to compress or stretch a spring. And for that we need to introduce something called Hooke's law. So basically the force it takes to press a spring, of course, is going to be variable. If you think about a spring, when you first start stretching it, it stretches pretty easily, but as it gets more and more extended, the force it takes to stretch it out gets harder and harder, or it requires a bigger and bigger force. Or same with your compressing. When you first compress it, it goes pretty easy, but as you start pushing harder, as it gets smaller, you have to push harder and harder. So basically, the force it takes to compress or stretch a spring is proportional to how much you've stretched it. So here's the formula: F equals some constant K times the X, which X is the displacement from normal length. So let's say that this is normal. So my spring, when it's just sitting there, it's normally 10 centimeters long. So in this problem, it took a force of 10 newtons to stretch to 20 centimeters. So since I stretched it from 10 to 20, the X in this example would be 10, because the X is the displacement, not the length of the spring, but the difference between the new length and the normal length. Okay, so in this example, the X would be 10. Okay, now in these spring problems, we have to have some kind of a way to find out what the constant is. Either they have to give us the K constant, or we have to be able to find it, and that's what this is doing. This says that it takes a force of 10 newtons to stretch the spring out to 20 centimeters. So knowing that the normal length is 10, that means this force of 10 newtons is equal to the K times the displacement. Now, the trouble, one of the problems here is that newtons doesn't play well with centimeters, because newtons is meters per, or it's kilograms times meters per second. So this has to be, anytime we're playing with newtons, we have to put our lengths in terms of meters. So 20 centimeters would be the same as point 0.2 meters. Okay? So if we divide 10 by 0.2, we get 200. So my constant, in this case, my string constant, is 200. So that means the force that it requires to stretch this spring is always going to be equal to, in this case, 200 times the displacement, how far I want to displace it. So you can see these problems are a little bit confusing, because there's really two distances. There's the distance that's involved in my displacement, in calculating the force, but there's also a distance that's involved with the normal work formula, right? Because the work formula is force times distance, right? So the way the spring works is going to look, the work is going to be force, which is 200 times displacement times the distance. So there's a point of confusion possibly there, of what distance is what. Okay, so we're going to answer a question. Let's say we're going to say how much work to stretch the above spring to I don't know, 15 centimeters. Okay. So now, why do we need integrals here? Because, as we said, every little bit of compression, the force is going to change, right? So the force is changing based on how much we've compressed it, right? So and the distance that we're going to compress it, of course, is also has to be calculated. So if we think about it, the way we're going to look at this is we're stretching this, not compressing, but if I stretch it, so if I stretch it all the way out to here, I'm going to stretch that first stretch. The first bit of stretching is going to have the same force. Then the next bit of stretching is going to have the same force, and then the next bit of stretching has the same force. So the little change at this time is going to be my distance. So my integral is going to be 200x times some little change in distance. Okay? Because so the distance something's being moved is not changing. It's the force that the distance that the force is being applied to, that's what's changing. So I break the distance into little increments instead of something involving the force into little increments. So that's what's different about this from the other types of problems. And of course, since we're going to 15 centimeters, now remember it's normally 10, so we're actually going from 10 to 15, right? Because the normal length of the spring is 10. So we're going to stretch it from 10 to 15. And that would be, so if we just evaluate that integral, it'll calculate the work done. So we're going to, let's see, that would be what? 100x squared, evaluated from 10 to 15. And then we'd have 100 times 225 minus 100 times 100. And, whoops, that's going to be 22500. Whoops. Minus. So we're going to have 125 or 12,500, and that would be newtons, because I'm remember to find the K we divided by, oh whoops, back up. Remember we said we had to be in meters, so this is a good chance for me to show that was, so really we want to go from 0.1 to 0.15, and so this should be 0.1 to 0.15, so then this would be 2.25. I thought that was kind of a big number. And this would be 0.01. Okay, so then that would be 225 minus 1. So it would be 224 newtons. Okay, so there's a spring example. So now you've seen, there's really the three type of work problems we're going to do. We're going to do ones involving where we're pulling a chain or a banner or a rope or something like that. And then the one where we're moving some kind of a liquid. And then these spring problems. So those are the three types of work done problems that we're going to be doing. And each one has a slightly different kind of way of calculating. And remember, the key is to keep in mind you're just figuring out, integration is just adding up a bunch of little things, so you have to look at the situation and figure out what are the little things that I'm adding up. It's also helpful to really ask yourself, why do I have to use integration here? Because that means something's changing as I go. So figuring out what is it changing, what's changing, that's how you determine the dx or the dy or whatever that little change is. All right.